Self-organized criticality can be observed in various other systems as well. For instance, consider an avalanche in a snow-covered mountain. Snow accumulates over time until the layer becomes so unstable that a small disturbance, like a skier moving across it, can trigger a large-scale avalanche. In social dynamics, trends and fads can spread rapidly through social networks. A small initial influence can snowball into a widespread phenomenon or cultural shift. In geological systems, volcanic eruptions can be seen as a form of self-organized criticality, where pressure builds up beneath the Earth's surface until a minor tectonic shift causes a major eruption. In cellular biology, the spread of signals within networks of cells can follow patterns of criticality, where a small signal can lead to a large-scale cellular response. Similarly, in computational systems, algorithmic models that simulate neural activity or crowd behavior often exhibit self-organized criticality, where minor inputs can lead to significant outputs, reflecting the underlying critical state of the system. Each of these examples demonstrates how systems in diverse contexts tend to evolve towards a state where small changes can lead to large and often unpredictable outcomes. Here are additional examples of self-organized criticality. Internet traffic. As network traffic increases, the system naturally reaches a point where even a small surge in data requests can cause significant network congestion or even a crash, akin to a traffic jam in a busy city. Ecosystem dynamics. In coral reefs, small environmental changes or stresses, such as rising sea temperatures, can lead to widespread coral bleaching and ecosystem collapse, demonstrating how ecosystems reach critical states. Biological evolution. Evolutionary processes in species populations can reach a critical state where minor mutations or environmental changes result in major evolutionary shifts or extinction events. Sand dunes. In desert environments, wind-blown sand forms dunes that can become unstable. A minor change in wind direction or sand deposition can trigger a shift in the dune structure, leading to significant movement or reshaping of the dunes. Social media virality. On platforms like Twitter or TikTok, a single post or video can go viral, spreading rapidly and causing a massive public reaction. This illustrates how social media content can reach a critical state where minor interactions lead to widespread visibility. Urban planning. In cities, the addition of new buildings or changes in infrastructure can reach a critical point where small adjustments or additions lead to large-scale impacts on traffic flow, housing markets, or community dynamics. Protein folding. In molecular biology, the process of protein folding often exhibits critical behavior. Small changes in the environment or protein sequence can lead to significant alterations in the protein structure, potentially affecting its function or leading to diseases. Cloud formation. In meteorology, the accumulation of moisture in the atmosphere can lead to cloud formation. Once the system reaches a critical point of humidity, even a minor temperature drop can trigger a significant weather event like thunderstorms or rain. Human behavior. In psychology and sociology, social behavior often reaches a critical point where small individual actions or beliefs can trigger large-scale social movements or changes in societal norms. These systems defy simple explanations, exhibiting emergent behavior that arises from the interactions of their many parts. Whether it's the synchronized flight of birds or the ebb and flow of urban traffic, the underlying principles remain the same. For decades, scientists have grappled with understanding how such complexity arises and the hidden order within these seemingly chaotic systems. Their quest has led to groundbreaking discoveries and new ways of thinking about the world. In the 1980s, a revolutionary concept emerged, self-organized criticality, or SOC. This idea transformed our understanding of complex systems. This theory proposed that complex systems naturally evolve to a critical state, balanced precariously on the edge of chaos. At this juncture, the system is highly sensitive to small perturbations. At this critical point, small events can cascade through the system, triggering avalanches of activity with unpredictable consequences. A single domino can set off a chain reaction, illustrating the power of interconnectedness. Imagine a sandpile. As you slowly add grains, the pile grows steeper until a single grain triggers an avalanche. This simple yet profound example encapsulates the essence of self-organized criticality. This, in essence, is self-organized criticality. It is a state where the system is poised on the brink of transformation, ready to shift dramatically with the slightest nudge. SOC offers a new lens through which to view the world, from earthquakes and forest fires, which can be seen as natural manifestations of this principle, to traffic jams and financial markets, where human behavior and economic forces interplay in complex ways. It suggests that these seemingly disparate phenomena share a common underlying principle. They are all driven by the same fundamental dynamics of complexity. This interconnectedness reveals the universal nature of SOC. By understanding SOC, we can gain insights into the behavior of these systems and potentially predict and mitigate the impact of catastrophic events. This knowledge empowers us to better prepare for and respond to natural and man-made disasters. The study of SOC is an ongoing journey, pushing the boundaries of our understanding of complex systems. Researchers continue to explore and uncover the mysteries of this fascinating concept. It challenges us to embrace the unpredictable nature of the universe and to appreciate the beauty and complexity that emerge from simple rules. In this dance of order and chaos, we find the essence of life itself, a testament to the intricate and wondrous fabric of our reality. The foundations of self-organized criticality were laid in 1987 by Per Bach, Chao Tang, and Kurt Wiesenfeld. These three pioneering scientists came together at a time when the scientific community was ripe for new ideas and breakthroughs. Their groundbreaking paper introduced the BTW Sandpile model, a simple yet elegant computer simulation that captured the essence of SOC. This model was revolutionary because it provided a new way to understand how complex behaviors could emerge from simple rules. This model, inspired by the analogy of a growing sandpile, demonstrated how a system could spontaneously organize itself into a critical state. The sandpile model became a powerful metaphor for understanding a wide range of natural phenomena. The BTW model consists of a square grid where grains of sand are dropped one at a time. Each grain of sand represents a small addition to the system, and the grid serves as a simple yet effective way to visualize the process. As grains accumulate, small piles form, and the system remains stable. This stability is maintained until the local slope of the sand pile reaches a critical threshold. However, as more grains are added, the piles grow steeper, and the system approaches a critical state. This critical state is characterized by the potential for sudden and dramatic changes. At this point, a single grain can trigger an avalanche of any size, cascading through the system and redistributing the sand. These avalanches can vary greatly in size, from small, localized events to large, system-wide collapses. What makes the BTW model so remarkable is that the system reaches this critical state without any external tuning or intervention. The critical state is an emergent property of the system itself, arising naturally from the interactions of its components. It is an emergent property of the simple rules governing the interactions between the grains. These rules are straightforward, yet they give rise to complex and unpredictable behaviors. This self-organization to criticality is the defining characteristic of SOC systems. It shows how complexity and order can emerge from seemingly random and chaotic processes. The BTW model provided the first concrete example of a system exhibiting SOC and sparked an explosion of research in the field. Scientists began to explore SOC in a variety of contexts, from physics and biology to economics and social systems. It demonstrated that complexity could arise from simple, local interactions, and that criticality was not a special or unusual state, but rather a natural consequence of self-organization. This insight has profound implications for our understanding of the natural world and the underlying principles that govern it. Today, the concept of self-organized criticality is applied to a wide range of systems, both natural and human-made. From the behavior of earthquakes and forest fires to the dynamics of financial markets and traffic flow, SOC provides a powerful framework for understanding complex systems. As research continues, scientists are uncovering new examples of SOC and developing deeper insights into the mechanisms that drive it. The legacy of the Bach-Tang-Wiesenfeld model lives on, inspiring new generations of researchers to explore the fascinating world of self-organized criticality. Self-organized criticality stands in contrast to traditional critical phenomena, which occur under very specific conditions. In traditional critical phenomena, such as the transition of water from liquid to gas, the system's behavior changes dramatically at a specific critical point. This critical point is reached by finely tuning a control parameter, like temperature or pressure. For instance, at its boiling point, water undergoes a phase transition from liquid to gas. This transition occurs at a precise temperature and is governed by the delicate balance between the energy of the water molecules and the pressure exerted on them. At the critical temperature, the system exhibits long-range correlations and fluctuations occur at all length scales. SOC, however, does not require such fine-tuning. Systems exhibiting SOC self-organize to a critical state without the need for external control. This critical state is characterized by a constant state of flux, with events of all sizes occurring without any characteristic scale. Unlike traditional critical phenomena, SOC systems are inherently out of equilibrium, constantly evolving and adapting to their changing environment. The distinction between SOC and traditional critical phenomena lies in the concept of self-organization. While traditional critical phenomena rely on external control, SOC systems are driven by internal dynamics that push them toward criticality. This fundamental difference has profound implications for our understanding of complex systems and their behavior. Self-organized criticality manifests itself through several key characteristics that distinguish it from other complex phenomena. These characteristics are not just theoretical constructs but are observable in a variety of natural and artificial systems. These hallmarks provide a framework for identifying and understanding SOC in a wide range of systems. By recognizing these features, scientists can better predict and manage the behavior of complex systems, from ecosystems to financial markets. 1. Scale invariance. One of the defining features of SOC is the absence of a characteristic scale. This means that the system exhibits similar patterns regardless of the level of magnification, whether you're looking at a small part or the whole. This means that events of all sizes can occur, from tiny avalanches to system-wide cascades. In practical terms, this could be seen in phenomena like earthquakes, where small tremors and massive quakes follow the same underlying principles. This lack of scale is evident in the power law distributions that characterize SOC systems. Power laws indicate that small events are extremely common, while large events are rare but possible, creating a predictable yet chaotic pattern. 2. Emergent behavior. SOC behavior arises from the interactions of many individual components. These interactions are often simple, but their collective behavior can be incredibly complex and unpredictable. The complex patterns and dynamics observed are not explicitly programmed into the system, but emerge spontaneously from the simple rules governing the interactions between its parts. This is seen in natural systems like ant colonies, where no single ant directs the colony, yet complex structures and behaviors emerge. 3. Critical slowing down. As a system approaches a critical state, its response to perturbations slows down. This is a warning sign that the system is nearing a tipping point where a small disturbance could lead to a significant change. This phenomenon, known as critical slowing down, occurs because the system becomes increasingly correlated, and changes in one part can have far-reaching consequences. For example, in ecosystems, the decline of a single species can ripple through the food web, affecting many other species. 4. Long-range correlations. In SOC systems, events are not isolated but can influence other parts of the system, even those far away. This interconnectedness is a hallmark of complex systems, where local interactions can have global effects. This interconnectedness leads to long-range correlations, where seemingly unrelated events can be linked through a complex web of interactions. In human societies, this can be seen in how social networks spread information or how global supply chains are affected by local disruptions. These characteristics, taken together, paint a picture of SOC systems as highly interconnected, constantly evolving entities balanced on the edge of chaos. They are dynamic and adaptive, capable of reorganizing themselves in response to changes in their environment. Their behavior is characterized by a delicate interplay between order and randomness, where small events can have profound and unpredictable consequences. This makes SOC systems both fascinating and challenging to study, as they defy simple explanations and require a deep understanding of complex interactions.